Okay, hi. So yeah, thanks RPG for the kind introduction. And yeah, so the talk got preponed because of course you all must be waiting for Professor Federico Capasso's talk. So let's hope that he will join sometime today. And let me first at the onset tell that as a part of this organizing committee with Professor Subhasish Gupta, Tarak and Professor Bimalendu, we decided that this particular field, which structured light and spin orbit photonics, something in India, we have a very small community. And of course, we had earlier some meetings on that, but not specifically possibly on this field. And we decided that it would be good to have a discussion meeting so that all the experts who are working in this domain would come and discuss. So therefore, the purpose is just not to deliver lectures, to eventually, we should basically interact, and this interaction should eventually lead to some fruitful collaborations possibly in future. And we are really happy that many of the speakers, all of them have agreed to give their lectures in a very short notice. And on behalf of the organizers, of course, we must thank them. And also to all the participants, basically, who have come. And we hope that we will have very stimulating next 2-3 days. Already we have been, we have heard Gautam speaking in the last talk and before that. And I hope we'll have this stimulating environment for the next 3-4 days. Okay, so this is something which I'm going to talk: angular momentum, geometrical phase, and spin orbit interaction of light, and which is of course one of the theme of this discussion meeting, that spin orbit interaction of light. Another part is of course on structured light. Of course, spin orbit interaction with structured light is also an avenue, but this is particularly what I have stated here, that coupling between the spin and orbital angular momentum degrees of freedom of light manifests in a number of exotic spin orbit photonic effects. Just like in condensed matter system, the electrons, spin and orbital degrees of freedom can get coupled and give rise to many interesting effects recently observed in condensed matter system, like spin Hall effect, the Aharonov-Bohm effect, and Rashba effect. All these, very surprisingly, have been seen in case of a classical light beam, which is otherwise looks a little surprising that a classical light beam should give such kind of effects, which has their origin in quantum mechanics, of course. But this is what we have termed as spin orbit photonic effects. So these are not only fundamentally interesting, but also they have led to a completely new field, because this has opened up a new paradigm of photonic devices also for control and manipulation of light at nanometer length scale, using this additional degree of freedom of light, which is angular momentum, like spin and orbital angular momentum, just like in spintronics in the condensed matter system. So this particular talk, I'm not going to talk about our own research. Of course, we have been working in this field now almost for a decade. I remember that we started working possibly sometime in 2011, 2012. And right now, our main focus of research is completely in this domain. But today, this talk will be mostly in pedagogical in nature. So I'm not going to talk about our own research. Towards the end, if I have some extra time, possibly we'll see, then maybe I'll give some glimpse of what we are doing currently in this field. And we will also introduce our group, research group, in this context. And of course, many of you, if you are interested also, then you can see some of the posters that we have put up, our students who are active in this domain of spin orbit photonics. So the purpose of this lecture is therefore to give the basics of this field so that you can appreciate some of the more scientific lectures on research topics. And this will be mostly on an elementary level for those possibly who are completely devoted in this domain. Possibly this might be a little bit, kind of an overview. But for those, I think in general, it might be useful that to give a background, to give some mathematical platforms also, or the experimental platforms where you can study all these effects. So let me just go ahead with this brief introduction. And so this is what I'm going to talk. Spin and orbital angular momentum. Already in the morning, Tarak has talked and Gautam has talked about orbital angular momentum carrying beam, vortex beams. So I guess I will not talk too much about it, but I'll just touch upon from the classical electromagnetic point of view, that part which is essential in the context of spin orbit interaction. So geometric phase, something which I will possibly talk a little bit in details, because all the spin orbit interaction effects that you will hear from many of our lecturers are related to this concept of geometrical phase. But I must say that as I go on, you will realize that the spin orbit interaction of light may also be mediated by geometrical phase and something which can be completely independent of geometrical phase. So I will mostly concentrate on things which are mediated by geometrical phase of light, right? But there is also another domain where the geometrical phase does not play a role. And we see very interesting effects like spin, momentum locking, etc., transverse spin, which is independent of the geometrical phase. And we have another lecture, of course, tomorrow to be given by Professor Subhasish Gupta, which will deal with the other part, which is like transverse spin and spin momentum locking, which does not involve the concept of geometrical phase. I thought earlier maybe we'll talk a little bit about weak measurement in optics, which we have been working for quite some time now, but possibly I'll not be able to talk about that. Towards the end, if I have, let's say 5-10 minutes, possibly, as I said, that we'll introduce our research group and maybe we'll talk a little bit about what we are doing in the context of spin orbit interaction of light. Okay, so this is what in more detail. So spin and orbital angular momentum of light. I'll talk about geometrical phase. The three variants of the geometrical phase: spin redirectional Berry phase, Pancharatnam-Berry phase, and geometrical phase associated with mode transformation. Then I will talk about the role of geometrical phase in spin orbit interaction, and we'll give examples of spin orbit interaction in symmetric systems like cylindrically symmetric systems, etc., and in broken symmetric systems. So one dealing with conversion between intrinsic spin angular momentum and intrinsic OM, which we'll define, and the other dealing with the symmetry broken thing like spin and orbital Hall effect of light. And finally, I will give the perspective that why it is becoming so important. What are the possible applications? Okay, so this book I'll just tell. Basically, this is three of us had written this book, and this book has a chapter exclusively on spin orbit interaction of light, and maybe we'll share some part of this particular chapter. And we have written also a couple of reviews on spin orbit interaction of light. That also possibly I'll follow that. And I must say that this kind of work that we started mostly started from the work of Bliock and others. So on the way, I'll give some very good references of Bliock, particularly some review, which kind of cover the thing that I'm going to talk. Okay, so this is very simple. Let me just give this simple thing that we know that light can carry linear momentum. So in the photon picture also, that each photon carry h cut k linear momentum per photon. Therefore, they can exert radiation pressure, and it also carries spin angular momentum. We know that circularly or elliptically polarized light. Sorry. So this is, yeah, so this is bet. Thank you. Yeah, that is. Okay, so this spin angular momentum is related to the circular or elliptical polarization. We will also define later on. So it can also exert mechanical torque on microscopic objects, particularly on birefringent object. Birefringent because this birefringent object will convert one spin to another spin, like left circularly polarized light can become right circularly polarized light, or linearly polarized light can become circularly polarized light. For example, if you take a half wave plate, we call it pi retarder. So a half wave plate can convert left circularly polarized light to right circularly polarized light. So on the process, therefore, it changes spin angular momentum from +1 to -1 per photon. So the two quantum of spin angular momentum are therefore transferred to this half wave plate, which therefore will rotate, or the torque is generated. So this is what is a mechanical action of this spin transfer, which we'll talk about a little bit. And then, so this is also follows from that photon picture, that if you have n number of photon, the z component of the spin, typically in the direction of propagation, is nh cut. And if the energy is nh cut omega, so the angular momentum to energy ratio is 1 by omega. Usually, if you have, let's say, spin 1 or spin -1. But if you have elliptically polarized light, so that we call the helicity sigma, which could be which can be between -1 and +1. So it is generally sigma y omega. So linearly polarized light will have no spin angular momentum, SAM. And so this is the other degree of freedom, which was the orbital angular momentum. It was recognized early 90s that classical light beam can carry this OM. And Gautam has been talking about it, that so basically it is not. So the first one, of course, is related to the circulation of the electric field. As we will discuss, that circularly polarized light leads to the rotating electric field in a given point of space, or as you see, as a function of propagation distance. So this one is not related to the rotation of the electric field, but it is related to the twisted phase front. When you talk about plane wave phase fronts are plane, right? So as it propagates, it is plane. So these twisted phase fronts as supposed to have this orbital angular momentum. And this kind of beams, as Gautam was talking, are called the vortex beams. So they have a center hole, that is intensity null at the center. And it can, in the case of spin angular momentum, you can only have, let's say, +1 and -1, and between +1 and -1. But L can has many values, so it can have so it depends upon how many twists it complete within a distance of lambda. So that is what it defines. So the question is that, is it possible to have a physically unambiguous separation of spin and orbital angular momentum for any arbitrary optical vector electromagnetic field? The answer is that in many cases it is difficult. It is not possible, but in some cases it is possible, right? So, and also are they separately physically observable? So coming to this question, so let me just start from the very basic electromagnetic picture of this spin and orbital angular momentum. Any form of the angular momentum of a classical electromagnetic field or a classical light beam, for example, given by the electric and the magnetic field, is related to the angular momentum r cross p, right? And p is therefore the linear momentum, which is proportional to the pointing vector e cross b. And if you talk about the linear and angular momentum of the field over a beam, so you have to integrate it over the beam. It's a two-dimensional integration. And so the angular momentum will be a two-dimensional integration like that, E cross B, right? So now let us think that if you have an idealized plane wave, which has, let's say, infinite extent propagating in the z direction, it is k is kz. So what it appears that basically this quantity, if you are thinking about the, let's say, angular momentum, z component of the angular momentum, so you have to have a component of this quantity in the transverse direction. That is the transverse component of the pointing vector, which is associated with the longitudinal component of the electric field. So ideally, a plane wave cannot have any angular momentum in the direction of the propagation, be it orbital angular momentum or spin angular momentum. But as I said, that this was well demonstrated that the circularly polarized light always carry a spin angular momentum. So this apparently look a little counterintuitive, but it is not counterintuitive when you think that if you think about a plane wave or a light beam, so you have this infinite number of small spin loops. This is called the PS, curl of S will give these spin loops. If you are talking about a plane wave, so they will exactly cancel out each other. But whenever you talk about a finite beam, or even if you, let's say, put a detector, you will always make it finite. So there will be net circulating spin loop here, and the curl of that will give the spin component in the z direction. So that is why that even if you take so nothing is plane wave is an idealization. Whenever you detect or you delete beam which has a finite extent, they will always have a longitudinal component of the electric and the magnetic field, which will lead to the z component of the spin angular momentum. So this is true for any finite optical beams. So this has a longitudinal field and transverse momentum components. So can be decomposed into Fourier components, like for example, a Gaussian beam. So you can decompose it into its Fourier components, kx and ky. So if you have a plane wave, of course, it is propagating, it's like a delta function, propagating in the z direction, only you have kz component. So it is k square minus kx square minus ky square. So kx and ky will be zero, ideally zero in that case. But let's say when you have a Gaussian beam or any kind of beam, So you will have a Gaussian distribution of the momentum as shown here in this picture. So it is like many plane waves, they are propagating in slightly different directions. So that gives rise to the transverse component of the pointing vector, that is some energy flow in the transverse direction, or the longitudinal component of the field. So this is what I have written here, that it gives rise to some longitudinal field component and transverse linear momentum, which is essential to have some component of angular momentum. Otherwise, we will never have a z component of angular momentum. So such a separation, as I was saying, that spin and orbital angular momentum, ideally, mathematically, it is difficult for any arbitrary electromagnetic field, but it is possible to have in so-called paraxial approximation. So I'll just give you a little bit of outline of that. So of course, many of you know that the paraxial approximation in very simple way, paraxial approximation is that, for example, if you write the electric field of light like this, f x y z e to the power I k z, which is the propagating part in the z direction. K is of course the wave vector. So this quantity f x y z, it means that in the paraxial approximation, the derivative of f with respect to z is much weaker than the transverse derivative. That means it is almost propagating in the direction, let's say you have a finite direction of propagation, it is not too focused, or it is not diverging too much. So it is almost propagating paraxially. So that is a condition when we typically loosely say we call a paraxial approximation. We can of course mathematically use that approximation to derive the paraxial wave equation. So that which I will not go in, many of you would know. So using this kind of paraxial approximation where these f quantities would satisfy the paraxial condition, one can actually separate out from using the classical picture of r cross p, where p is the pointing vector related to E and magnetic field and electric field. You can separate it out. And how it is done, basically, you can use Maxwell's equation and you can replace B by E from there, and then you can use paraxial approximation in that, and then you can write the z component of the angular momentum density like this, E cross R cross grad E. So it is like that corresponding quantum mechanical operator, which is given as x del del y minus y del del x, mathematically speaking. So this is like in a symmetric system, it is like del del phi. If you are talking about, let's say, a cylindrically symmetric system, so this is like del del phi, whereas the other part, which will give as E star cross E, as we will see later, that this is related to the circular polarization. So this is related to the x and the y component of the vector fields, fx star fy minus fy star fx. This is somewhat will come later, that this is the so-called fourth component of the Stokes vector. So which is a measure of the circular polarization or ellipticity of light. So this can be separated like that for paraxial beams, so that when this part will give you the orbital angular momentum. For example, the kind of beam what Gautam was talking about, that which has a phase like this e to the power IL phi, and if unit vector, it is the corresponding vector part, which is the polarization part, and UR is its radial dependence. Like if you take a Gaussian, it will have a Gaussian envelope like that. So it will give, according to this definition, an angular momentum of L, and because del del phi of this will give the vortex charge L. So this follows quite simply from simple calculations using the classical theory. And this one, as we will come later on, is related to the forced stroke vector element, that is a measure of the circular and elliptical polarization of light. And just to show that the thing that we were saying, that if you have a, in the photon picture, using this electromagnetic field picture also, you can show that if you just follow this calculation, that the angular momentum to the energy ratio becomes sigma plus L by omega, where now L is added to it. And so if L is equal to 0, then it will again become sigma by omega, which we just for a single photon in the photon picture you give. So therefore, it also gives you the similar kind of things that follows from the pure classical calculations. And this is what we define the wave velocity and the spin angular momentum density. So I have just written in terms of the electric field, but it has both electric and the magnetic field component. So E cross E star plus H cross H star. So the spin angular momentum has both electric component, electric contribution AC and SM. And this is how we define the density of the spin angular momentum. Of course, you normalize by the energy density. So this is some elementary definitions which many of you know. Now I'll maybe go a little bit about the polarization optics, which is basically needed to understand and interpret all that you will be hearing in the next few lectures, or all that related to spin orbit interaction of light, some of which possibly Gautam was also talking about. So many of you know, but still you see that in the field description, the polarization of light can be represented. Again, that's what I have written. Assumption is that plane waves are elementary beams where the polarization and spatial mode are separate. This is where you can use simply this kind of algebra without much confusion, that where you can separate out the spatial mode and polarization. So the polarization can be described by the two component electric field. And again, we are thinking that the longitudinal component is very weak, but in principle, you can do a 3x3 system also, but we'll restrict ourselves to these two transverse component, EX and EY. So it has an amplitude part and a phase part. So this amplitude part is given by this and the phase part is given by that. And all kind of polarizations are represented by this amplitude and the phase differences. For example, a horizontally linearly polarized light in this notation can be given a state vector as 1, 0. Vertically will be 0, 1, 45, 1 by root 2, 1, 1. Left and right circularly polarized light will be 1 minus I and 1 I. That's what we'll be using later on. And any arbitrary elliptical polarization can be written by this. So theta and epsilon are the azimuth and the ellipticity. So tan of epsilon is the ratio of the minor to the major axis, right? So that is how you define. So the limiting values of this ellipticity is minus pi by 4 and plus pi by 4. Plus pi by 4 for right circularly, minus pi by 4 for left circularly polarized light. So this is typically, you write the state vector for this ideal field description. But of course, what you assume here is that the field to be perfectly coherent, so that this phase difference that you are talking about is completely independent of time, right? So therefore, and you are using a pure field description. So these are kind of pure states, but in practical scenario, you will have something different also. But again, before I do that, so any interaction with this polarized light with any material medium can be represented by this 2x2 matrix, which is called a Jones matrix. So all the polarizing optical elements have their characteristic Jones matrices, some of which we'll show in the context of SOI, right? But as I was saying that this deals with pure polarization, because you know that there was no sort of idealized scenario that the phase difference between these two is constant, almost like it is independent of time. But we know that coherence limits that, because nothing can be like that. So therefore, it is important that we define something in terms of so-called intensity, which is a time average. So this is just done by the so-called 2x2 coherency matrix. So the coherency matrix is basically written as the direct product of the Jones vectors, and you take the time average. Direct product means Kronecker product. It is like EX, EX star, EX, UI star, EY, EX star, and UI, EX star. So you see, all of these have the dimensions of intensity, but all of them are not intensities, right? Because some of these quantities might be complex. But if you do a permutation and combination of this, then it becomes intensity. All of them are measurable intensities. For example, these and these are measurable intensities, but these two are not. But if you add them or subtract them, they can be measurable intensities. So that is what is done to define the Stokes, so-called Stokes vector through these coherency matrix elements, so that if you add, let's say, these two, this will give you the total intensity, Ix plus Iy. That is, if you put a polarizer, horizontal and vertical, add them, then you will get the total intensity. And you take a difference between them, right? And then you take combination of these two. That means EX, EY star plus EY, EX star. So this is also, this will become an intensity because it becomes real part of EX, EY star. So this is a dimension of intensity, and it is a real part of some complex quantity. So this is an intensity. And this can be easily shown that this is actually another basis, which is represented by a basis X plus Y by root 2. That means one is X, another is Y. And when I take this, so it is difference between the X plus Y by root 2 and X minus Y by 2. That is, it is plus 45 and minus 45, something like that. And the fourth quantity, which is again using this EX, EY star minus EY, EX star, now with this I. So it will give you imaginary part of EX, EY star, mathematically, twice imaginary part of EX, EY star. So this is also an intensity. And again, you can show that this can be represented in a different basis. So these two are represented in a XY basis. These require another basis, which is X plus Y by root 2 and X minus Y by root 2, which we call as plus 45 and minus 45 in terms of polarization. And this will require the basis of circular polarization. That is x plus IY by root 2 and x minus IY by root 2. I because there is a phase difference of pi by 2 between x and y. So this is as simple as this. So you can actually write this so-called Stokes vector, which are perfectly measurable experimentally. So therefore, what you will do is that you will put a polarizer and you rotate to x and y and will sum this intensity, take a difference of this intensity, put the polarizer at plus 45 and minus 45 and take a difference of them. And to detect this, you have to do something more. You have to take a polarizer and a quarter wave plate to make it circular left or right, okay, and take a difference between them. So this is just elementary definitions of this. So in terms of the Stokes vector, as I said that it can encompass also mixed states or completely even unpolarized states also, because now you have taken the time average. Unlike the Jones case, it is now you are dealing with the complete set, right? If you are dealing with, let's say, partially polarized, partially coherent, right? You never have 100% polarization, so it can encompass such kind of situation. Which one? So helicity has between -1 to +1. So, but in case of a electromagnetic field, you are talking about the degree of this can become any fractional value also. And so because you are talking about the field, basically you are defining the sigma helicity of a field, not of a photon as such. So this is just difference in the left and the right component of the light divided by the total intensity. So it can also assume fractional values, right? So elliptically polarized light will not have integer values of sigma, right? Okay. So so for example, these states horizontal polarization is 1 1 0 0. Unlike the Jones, it's like the Jones. Basically, it is like in a actually higher dimension. You can say that it was 2-dimensional. Now you are doing actually in 3 dimensions. We have additionally added something in a different space, which we call the polarization state space, which we will come to in the context of spin orbit interaction. So vertical polarization will be 1 minus 1 0 0. Plus 45 is 1 0 1 0. Circular will be 1 0 0 1 1 0 minus 1. So unlike the Jones, here everything is real because it is based on intensity. That is the only difference. And also degree of polarization, because now you are also dealing with partially polarized light. So degree of polarization is defined like that. Completely unpolarized light is like 0 0 0. It is like you put any polarizer or a plate, rotate, whatever you do, there is no variation of intensity, practically speaking. So again, just like Jones transformation, Jones matrix is a 2x2 transformation matrix. Now it is a 1x4 vector. So you'll have 4x4 transformation matrix, which is called a Mueller matrix, which is measurable in terms of the intensities. And using this simple connection between them, you can also connect the Jones and the Mueller matrices by this. So this, you see that the Stokes vectors can be related with the coherency matrix elements, or you can call it coherency vector through this matrix A. So this matrix A comes in mathematically like this: A, J, direct product of J, A inverse, right? But remember, there is always, of course, a Mueller matrix for all the Jones matrices, but all the Mueller matrix does not have the corresponding Jones matrices, because Jones vector deals with pure state. Jones matrix deals also with pure interaction, that is polarization preserving interaction. But Mueller matrix can include both polarizing preservation and depolarizing interaction. So all the Mueller matrices have not their corresponding Jones matrices. So these are called Mueller-Jones matrices, like the pure interaction. What you know, like a polarizer is a Mueller-Jones matrix. A wave plate has a Mueller-Jones matrix. A is like mathematically how we have written is that I said that using these elements of the coherency matrix by doing permutation and combination, I define the Stokes vectors. Yeah, so that is how we define it. So that is why mathematically, because see, Jones matrix is easy to construct. We'll see that. Mueller matrix is not directly easy to construct. So basically, if we connect them, then it becomes very easy to write. Yes, so that is, there is a one-to-one connection only between the pure effects. For example, if I am talking about an input state and it transforms to the input state to another pure state, so that is mapped by a Jones matrix. That is also mapped by a Mueller matrix. But there are cases where actually there is loss of polarization, and Jones calculus cannot deal with that, because Jones calculus only deals with in which. So that's what I'm saying, that here what you have written is that in terms of the two phases, for example, which is completely independent of time, right? So when you talk about, let's say, incoherent sources, time averaging will lead to partial polarization also, right? So ideally, no source of light can give you 100% polarized light because it is limited also by the coherence property of the light. Okay. So that also, no, that he wanted to know that how it is coming. It is coming from the time average. So I'm saying that Jones gave you only 100% polarization. So all these have corresponding Jones vectors. But if I am talking about this, it does not have any corresponding Jones vector. This is completely unpolarized light. You cannot write the corresponding Jones vector. So there are some cases you can write the corresponding Jones matrix of a Muller matrix, but some cases you cannot write. But all the Jones matrices have their corresponding Muller matrices, right? So this is just to give you set the background for what we'll show there. Another interesting geometrical interpretation which we will be using later on in the context of spin orbit interaction is the so-called Poincare sphere representation. So we have now defined a different geometry, like in a different space. When you are dealing with the Cartesian space X and Y, we are defining the Jones vector as Ex and Ey. But we have constructed a different space, which we always refer to as polarization state space. So the geometrically you can represent it like this. So these are the four Stokes vectors Q, I, Q, U, V. You remember that is I is the total intensity, so that is redundant. I can normalize it by the total intensity. I can make it 1 Q, U, V, right? So that is total intensity, therefore is redundant. So when we do a geometrical interpretation, I write in terms of Q, U, and V. So these are the three coordinates like my X, Y, and Z coordinate, right? So this is a different space that we are defining. So any polarization state can be written in this Poincare. So this is called a Poincare sphere. So for example, any linear state will be in the equator region. And so by the definition, because the two poles are the left and right circularly polarized light, because V coordinate you are using as a Z coordinate light. And so this is right and this is left circularly polarized light. This is horizontally polarized light here. Opposite to that will be vertically polarized light. This is plus 45 degree polarized light, minus 45 degree. All the different polarizations are in the equator range. As you go from equator to the poles, then you slowly go into the elliptical states. Finally, you get the two poles are the left and right. Yeah. So all these states will lie on the surface of the sphere, but partially polarized light will lie inside the sphere. So they will not lie in the surface of the sphere because they satisfy Q square plus U square plus V square is equal to 1 is satisfied. So this is a sphere satisfied by the pure states only. But for the partially polarized state, Q square plus U square plus V square less than 1. So they will lie inside the sphere. And in fact, the center of the sphere is the corresponding state 0, 0, 0, whose coordinate is 0, 0, 0, which is the unpolarized state. This one? Yeah. This is simply basically. Yeah, so AS represent pure and mixed states because you are doing this time average quantities, right? Because see, ideally, as I was saying that these two quantities, they are always in phase, like you are writing in terms of phase, but you are not considering phi x as a function of time, right? So that you have completely dropped. As soon as you do a time averaging of that, because these are all angular bracket I'm using for time averaging. So that feature is gone. Now you are actually in this, but I'm saying that for a pure state, you can always map the corresponding Jones vector into the Stokes vector or the Jones matrix into the Muller matrix. Pure states and pure effects polarization. Okay, so this is how you represent them. I will come to that. This useful geometrical interpretation in the context of, because spin orbit interaction always deals with the geometry, so that will be useful to interpret in terms of the geometry. So this is what basic thing that I wanted to do. And another thing I wanted to just tell you that these rotation matrices have very useful consequences in spin orbit interaction. For example, if you write a Jones matrix in one reference frame of, let's say, something, and you want to represent that in another reference frame, so you will use this similarity kind of transformation using rotation matrices. Right? For example, if you take a wave plate whose axis is oriented at say 0 degree, you will write the Jones matrix. And then if you want to write this Jones matrix in another reference frame where the axis is rotated by theta, so you will actually use this relation that J prime, which is in the rotated coordinate, is R inverse theta JR, where R is a simple rotation matrix, 2 cross 2 rotation matrix around the Z axis. And if you use this simple relationship between Jones and Muller, pure this thing, then you will see that this rotation will also give a kind of a rotation matrix in this new space, which is now, if I drop the first row and the first column, which is redundant, as I said. So this also represented rotation matrix now around the V axis geometrically. So this rotation matrix is a rotation of the QU coordinates of the Stokes vector around the V axis, right? So that it also represents a geometrical rotation in the coordinate space, also represent a rotation in the Stokes vector space, but a theta rotation corresponds to a 2 theta rotation in the Stokes vector space. So that means, for example, if I am taking, let's say you talk about optical rotation, so let's say this is a polarization, it is rotated by an angle. So this angle, let's say in physical, it is rotated by a theta angle, so that will also suffer a rotation in this by 2 theta angle. So that is how the geometrical interpretation is in this new space. So let me just give example of different effects which will be useful in the spin orbit case. One is, of course, the retardance effect, which is called the birefringence, where the phase shift between two orthogonal polarizations, which can be written like that in the Jones matrix. It is where I phi x 0, 0, it is where phi. Very simply, you can write it. Where the phase retardation is delta phi x minus phi 1. Now it has a axis which is, let's say, oriented at theta, because by default you have chosen this is a diagonal matrix. So therefore, the axis of orientation is at theta equal to 0 degree. But if I rotate it, let's say I rotate the wave plate, then I can represent the corresponding Jones matrix by these rotation matrices, and the corresponding expression will become this, where theta is a rotation. For example, if you take a which axis? So Z is the propagation direction, and your wave plate is like that. So let's say the anisotropy axis of the wave plate, like the fast or the slow axis, is oriented along this. So then the matrix is like this one, a diagonal one like this, for example. Now if I, in the principal frame, this is called, you can in the material frame. And if I rotate this in your laboratory frame, the matrix will become like this. So this is how you will write. So for example, a quarter wave plate in this definition has a matrix like this, 1, 0, 0, I, right? So that's what I'm saying, that if in its own reference frame, it is diagonalized, this effect particularly. But it is because in its own reference frame, you are defining the anisotropy axis to be at the 0 degree, for example. But that 0 degree may be at some angle theta in your laboratory frame. Then you have to do this rotational transformation to represent it in the laboratory frame. And as we will see, that at the heart of spin orbit interaction are many of these rotations, because rotations have non-trivial effect in context to geometrical phase. So for example, a quarter wave plate is written like that. A quarter wave plate can transform linearly polarized light into circularly polarized light. So you will see that linearly polarized light has spin angular momentum 0, and it will now transform into light which has spin angular momentum plus minus 1. So therefore, the angular momentum balance has to take place, and some angular momentum has to transform into the quarter wave plate. So it will rotate. So in this case, one quanta will be transferred. A half wave plate on the other end is like 1, 0, 0 minus I. So it will be I pi, it will become minus 1. So it will transfer now right to left. So it will transfer 2 angular momentum into the, as I was saying, giving example of that, right? So this is an half wave plate. Right. So another thing is, of course. Yeah, these are measurable, but you cannot measure the electric field. You will measure it through the intensity. Corresponding Mueller matrices are measurable. All the wave plates, etc., everything is measurable. These matrices are measurable, but not the field-based matrices, because it is electric field, but you will detect the intensity. That is why the intensity-based measurement is intensity-based definition is useful also. It's not only conceptually better, but also useful. Right. So another important effect which will be useful in the context of spin orbit interaction is optical rotation. Many of you, of course, know that these chiral molecules has right-handed or left-handed arrangement. So they sense left and right circularly polarized light differently. So they give a phase difference between left and right circularly polarized light. If you use simple Jones calculus, you can write any linearly polarized light as a superposition of left and right. 1I plus 1 minus I will give you 1, 1, 0. And if you give a phase difference of plus psi and minus psi to left and right, you will see that the polarization state will be rotated to cos psi sin psi. Simple algebra. So therefore, the circular retardance effect will rotate the polarization by an angle psi, and which is related to the phase difference of plus psi and minus psi, that is 2 psi phase difference between left and right. Remember this, any rotation of the polarization vector is necessarily interpretable in terms of the phase difference between left and right circularly polarized light. So this will be very useful in the context of the geometrical phase, as we will come later on. So another kind of device which is basically, you can say, the polarizer. So these are called diattenuator. So this will absorb different polarization. An ideal diattenuator is a perfect polarizer, 1, 0, 0. So if I start with, let's say, circularly polarized light, it will convert to linear. So therefore, again, some angular momentum will be transformed to the polarizer, because it will transform into linear. So again, a polarizer written in its own reference frame, that is also another axis of polarizer. If you rotate it, you can actually use the same rotation matrices to represent it in the laboratory frame like that. As I said, that this is also related, will be useful in the context of spin orbit and geometrical phase. So this, of course, Gautam has talked about the intrinsic orbital angular momentum, but that is another variant of the orbital angular momentum, which we called extrinsic orbital angular momentum. So of course, angular momentum is related to this quantity r cross p, r cross e cross b. So this extrinsic OM is related to the trajectory of the beam or some symmetry breaking or truncating of symmetric beams. So in essence, you can say that if I use my coordinate system to calculate this quantity over the beam and I displace it by this small quantity r0s, let's say r0y, there will be a change in this calculation of the angular momentum delta jz, so which will be r0s this, and you will integrate it over it. So if for any choice of my coordinate system, this delta jz is 0, then I will say that the beam's angular momentum is completely intrinsic. It does not have any extrinsic component. But if this quantity is non-zero, then we will also call this an extrinsic orbital angular momentum. And it was shown also that to have only intrinsic contribution, so total transverse momentum must vanish, because that is a symmetry which is related to that. And so that, for example, if you take a vortex beam, so it is such a way symmetric that if you integrate it over this total dx dy, they have transverse momentum, but if you integrate it over the entire beam, so they will vanish. These are the kind of beams which will only give intrinsic orbital angular momentum. But if you break the symmetry of the beam, for example, if I truncate some part of the vortex beam, then this symmetry is broken, and therefore this quantity will non-zero. And that is related to the so-called extrinsic orbital angular momentum, which we'll later on discuss that is related to something called spin Hall effect of light. So this is what I was saying, that there is an equivalence. This is the polarization picture, that if you have a half wave plate, which is called a pi retarder, it will transform left circular to right circular. We discussed this thing earlier. Again, coming back to the same question, conservation of the... No, I am not talking right now at the conservation of the moment. I said that. No, but I said the conservation of the momentum you will be there if you are if I choose a particular coordinate axis and I do all my calculations on that, then I can look into the conservation of the momentum. But that is also from literature. Right. But if you don't, if you break the then that will not be conserved. That broken symmetric system. We'll come to that. We'll come to that. And so, because I'm going a little slow. So this is, as I was saying, that this is the Bethes experiment, that a half wave plate will transform left to right, and it will transfer two angular momentum quanta into this. A similar analogy is a pi mode converter, which is made up of two cylindrical lenses separated by a focal length f. So it will transfer plus L to minus L. So it will also give torque to this pi mode converter. And those kind of things you can see in optical trap. Ion will be talking a lot about this, that how microparticle, in case of a bidifferential particle, you have the spin angular momentum, how it is transferred, it will rotate around its own axis. In case of OM transfer, it will revolve around the axis of the beam. Okay, so now I think most of the basic things is done. We'll come to geometrical phase and spin orbit interaction of light. So when you talk about phase, of course, we talk about the dynamical quantity, which is dependent on the path length and the refractive index of the medium. But as we will see that, and many of you know, that something which is completely independent of the path length, and it is only determined by the geometry itself, the topology of the evolution of the electromagnetic wave. Now, there are two kinds of topologies we already have discussed. One in the coordinate space that we have shown, that if we have, let's say, defined the light in a Cartesian coordinate and it can go in a trajectory. The other is that where it actually follows a trajectory in the polarization state space. That means it can continuously change the state of polarization. So there are two variants of that. So evolution of polarization state, but again, I'll come to that, that there are two kind of angular momentum also gives geometrical phase, the spin angular momentum or orbital angular momentum. And each of these has two different kind of geometrical phases. One is related to the evolution in the coordinate space, other is related to the evolution in the polarization or orbital angular momentum state space, which is like the Poincare sphere. So this is called the spin or OM redirectional Berry phase, and this is called the Pancharatnam-Berry type phase, where you are talking about continuous change in the angular momentum state of light. So that is also a change in the trajectory of light in some other space. So this is the first kind of example. This is taken, of course, from Bleock's Nature Photonics review, and in our book also we have used similar kind of analogy. So let us take a twisted fiber. A fiber when straight, it's completely, let's say, isotropic fiber. It does not change the polarization of light. So if I launch horizontally polarized light, it will pass as horizontally polarized light. But if I twist this fiber means I give a pitch angle to this fiber, then you see that each time it will complete one turn, the direction of the propagation, which can be represented by the k vector, it will come back to the same direction. But because of the nature of the three-dimensional nature of the twist, the polarization vector will not come back to the same direction again. So that is a slight rotation of polarization because of this twist. Each of these turn will do that. So this rotation is, let's say, theta in this case, and it will depend upon the twist angle. Now, as I said, that any kind of rotation of polarization is necessarily interpretable as a phase difference between left and yes.
This one you were saying the k is side k.
Yes, k is changing. It comes back to the same k, but when you do that, the polarization which is actually perpendicular to k, it does not come back to the same state.
But now, why should I bother with it?
See, quantized value is one thing. So you can also talk about quantized geometrical phase, but this is in general a geometrical phase. So in fact, when the notion of the geometrical phase was given by Berry, it was of course for a quantum particle. But the most easy way that you can see it is for a classical light beam. So that is what we will be talking about, that why it is special, because it leads to so many interesting effects, and in context to fundamental effects and also in context to application. So that will become clear later on. You go ahead and yes. No, I said that I take a fiber, straight fiber, and then I make a pitch angle of the fiber, just like a corkscrew phase, and I twist it, right? So you see that due to this twist, the polarization, our input and output polarization will change. Total internal reflection by through it. No, that, see, there are also, see, ideally, if you take a multi-mode fibers, there are a lot of change of polarization. But single mode fibers mainly, mostly keep the state of polarization intact. There are many other ways also keep the state of polarization intact. But I'm saying, thinking about an idealized situation where the locally polarization is not changing, right? That locally, there is no change in the polarization. Locally, polarization will be changing, only the fiber material is bidirectional. Right? Because as it propagates, linear will turn into elliptical, then circular, elliptical, if it is bidifferential. If it is non-bidifferential, it will not locally change. So this is the kind of thing I have written that. So this is then an adiabatic evolution. Locally, the fiber does not change. If I go with the ray of the light myself, the observer, I always see the polarization is perpendicular to me, right? But if you see globally, then that is a rotation of the polarization taking place. And as I said, yes.
How do you take care of adiabaticity here?
So adiabaticity here in terms of the change of the polarization. Locally, the polarization here.
In terms of your fiber, so you should slowly or
that is also, and so adiabaticity in this context is the change of the state of polarization. So if you make a fiber and turn it slowly like that, but if you, let's say, make the fiber of some bidifferential material, locally it will change, so that adiabatic thing will go, The polarization state will not change locally, it will change slowly when you go basically look from the global reference frame. That is the adiabatic evolution here.
Geometry because of the turn of this fiber, right?
Right.
So that is like parameter space. of
Space.
the-
So that the fiber that you make, let's say you can make it such a way that it is going slowly, like the turn is slowly like that. That you can do, define. Slow. So that is defined through the this pitch angle of the helix that we are talking about, and in context to the momentum that you define, because it is defined with respect to the k, change in the k vector. So what has to be defined? Defined in terms of the k vector when you say slow or fast, right? Okay. So so helicity of the wave does not change locally. So that means right circularly or left circularly, they do not change locally, but they evolve as it goes. So there is a net change in the polarization. And as I said, that so rotation of the polarization is necessarily interpretable as a change, as a phase difference between left and right circularly polarized, right? So as if I launch a left circularly polarized light here and right circularly polarized light here, so they will acquire different phase here, right? So that is why you are getting this rotation of the polarization. So for example, if I launch X polarized light, it can be written as a superposition of left and right, right? And if it is rotated, let's say by this angle theta, it is necessarily taken a phase I theta, that is theta for left and minus theta for right, right? And this phase theta, plus theta and minus theta, we talked about that phase earlier for a chiral system, which was a dynamical phase. Here it is completely geometrical because it is decided by the pitch angle of the fiber and how you rotate it, right? So that is why you can term it as a geometrical phase. In terms of this representation in the K sphere, so let's say if I represent in the Kx, Ky, Kz, that's what we are saying, that it can be written in terms of this coordinate sine theta cos phi, where theta is the angle with respect to the local propagation direction, so which is the pitch angle of this helix, and phi is the azimuthal angle, right? So if you see that this geometrical phase, so it will actually make a closed loop in this K sphere, but during this process, it will acquire a geometrical phase, which is exactly the solid angle which will subtend at the center of this sphere. And this turns out to be 2 pi, let's say 1 minus cos theta. You see that if theta is 0, that is no twist angle here, then it will vanish. And again, theta is equal to pi by 2. That means now if you look the fiber in the same plane like that, it will make a 2 pi this thing. That means it will come, the polarization will again come back to the same state. So that is an accumulation of 2 pi phase, but you will not be able to discriminate. So if you have n number of such terms, then your geometrical phase will be 2 pi n 1 minus cos theta. This is for pure state. The mixed state is complicated, because mixed state will have basically unpolarized component. So
things can go down.
So it can be different also, right? Okay. So another variant of the phase. So this is one, as I was saying, that it is a trajectory in the coordinate space. The other is a trajectory in the Poincare space. The best example I always give is that half wave plate, as I was giving. The half wave plate, if it is oriented at an angle beta, if you write the half wave plate, if you remember that 1, 0, 0, minus 1, and then you multiply the rotation matrices, the Jones matrix of the half wave plate will become like this, where beta is the orientation angle. Let's say if I start with a X polarized light, output will be cos 2 beta, sorry, this will be sin 2 beta. This all of you know that if I take a linearly polarized light and if I rotate the half wave plate, the output polarization is rotated twice the angle of the wave plate. That is, everybody knows that. So this is also an example of the geometrical phase, because there is also a rotation of polarization which is independent of the material property. This rotation is completely determined by the orientation of the wave plate, which is again sets the geometry, right? So again, you can check that if I start with left circularly polarized light and if I pass it through this wave plate, then I'll get a phase factor of twice beta for left circularly polarized light and minus twice beta for right circularly polarized light. So there is a phase difference of 4 beta between left and right circularly polarized light, and therefore it will lead to rotation of 2 beta. So this is also an example of the geometrical phase. There's a beautiful experiment which was done by Simon and Kimball in 1988. So this is a beautiful experiment to show this geometrical phase in a Michelson interferometer, because of course geometrical phase you will be able to see when you see in an interference experiment, because that is how we detect phase. So what they did is that, so they took a laser. This is a conventional Michelson setup, that mirror 1, mirror 2, and you see the fringes here. And you put a polarizer instead of conventional Michelson. They put a polarizer, a beam splitter, and then a fast quarter wave plate. The fast quarter wave plate is oriented at 45 degree. So if I have a linearly polarized light, let's say 10 state, it will make it circularly polarized. Then they put another quarter wave plate whose orientation axis I can vary, right? And after passing this, the second quarter wave plate, it will again become linearly polarized, but not like the initial state 1, 0. It will be linearly polarized with some arbitrary angle beta, which will be set by the orientation of the wave plate. Then when it reflects and comes back, that linearly polarized light again goes through this quarter wave plate. So it will become circularly polarized light again. And then again through the first quarter wave plate, it will come back to the initial state, right? So in this process, it will make a closed loop in the Poincare sphere. So it started from here, it goes to circular polarized after this, then it comes to the equator again. So that means it will become linearly polarized. When it returns back, it traces back its path, it will go to right circularly polarized light, left circularly, and then it will come back to the initial state again. In this process, it will make a loop like that. And the geometrical phase is half the loop that is subtended by this loop in the subtended at the center of this sphere. Half, because you remember that in the case of the K sphere, it was exactly the area subtended by this solid angle. This is the subtended by this solid this area at the solid angle, but it is half because you remember that beta rotation in the coordinate space corresponds to 2 beta rotation in the Stokes space. Yeah, so, Bhandari's experiment, I'll come to that. Bhandari's experiment was a one step also, very interesting thing, which is related to, I'll just, because I'm going a little slow. In a different geometry. And they also look, I'm just telling you that they also suggested that now see, so this geometrical phase is 2 beta, which is related to the orientation angle of the wave plate. Now, the same thing you can think about a half wave plate also. The same experiment that Simon and Kimball did and suggested, and they did a second part, which I will tell that the second part is related to spin orbit interaction more closely. So a half wave plate, also if you, now you think that is, now let's say this is fixed, this wave plate is, beta is changing. Now if beta is changed, beta keeps changing, then the geometrical phase will keep changing as a function of time, right? The same situation arises when you take a half wave plate, single half wave plate. So if I start with a circularly polarized light, and if I rotate it, so you'll see that if there is a constant rotation rate, d theta dt, then of course geometrical phase proportional to the orientation angle. So the geometrical phase will go as 2 tau t, where tau is this rotation rate, d theta dt, right? So this will lead to a change in the frequency of the light, because this plus minus, because for left circularly polarized light, it will transform into right circularly, but it will give a geometrical phase of +2 and the other will give you -2. So this will lead to a change in the frequencies, shift in the frequencies, delta omega, which is omega plus minus this 2 in the 2 times the rotation rate, right? So this is called a rotational Doppler shift, depending upon the input spin angular momentum of light. Generalized, if you can generalize it instead of half wave plate, if you take any arbitrary wave plate, so this quantity is difference between the input and the output spin. So in case of the half wave plate, the difference is +1 -1, so it is 2. But if you take any other wave plates, maybe if you take a quarter wave plate, then it is between circular to linear, that is S minus S0 is 1. So this is a frequency shift, which is actually also this Simon and Kimball suggested is a dynamical manifestation of the geometrical phase. As will come along that the spin orbit interaction effect or the spin Hall effect, etc., that we will see, they are actually the spatial analog of this dynamical manifestation of the geometrical phase, this rotational Doppler effect that was seen earlier. So there is also another variant of geometrical phase associated with the mode transformation. In a much similar way as we define the polarization, the different polarization state can be written by the vector addition of each other. Like if you have this polarization state, it is written as a horizontal minus vertical. This state is written horizontal plus vertical. Then circular is horizontal plus I into vertical. Right circular is horizontal minus I into vertical, something like that. Similarly, in the mode also you can write like that. Let's say if you're talking about the HG01 mode, this is let's say HG01 mode, this is HG10 mode. If you subtract them, you like the orientation of the mode will be at 45 degrees, just like the linear polarization. Similarly, if I have let's say a LG, it can be written as a sum of HG01 plus IHG10. Just like you write circular as a sum of 2 linear polarization with a phase difference of pi by 2. So this close analogy gives a similar kind of Poincare sphere, which is called the Bohm Poincare sphere. So like here, the linear states are all lying in the equator. Here all the HG modes are lying in the equator, and the top and the bottom are the LG modes, +1 and -1. And there are also higher order point mode conversion picture basically, so measuring is difficult, because obviously you have to pass it through some mode blocker, which will just like the polarizer, and mode converters can be used. So mode converter just define them. So I will come to that is also defined. So similarly, that I was saying that if I think about the rotation of the linear polarization like that, the mode while going through a twisted fiber will also be rotated like that. And that rotation can also be represented in terms of geometrical phase for the LG +1 and -1. So this is the corresponding spin redirectional OM redirectional geometrical phase. So this is related to the trajectory.
But here you can have
Multiple waters, and so you can have 2 quanta, 3 quanta, 4 quanta, you have more control, right? So that is good. Okay, so there are, as Professor Gupta was saying, that there are suggestions that this analogous experiment which Simon and Campbell did. So similar kind of experiments, like for example, this rotational Doppler thing that I was telling about, that a half wave plate is represented by a pi mode converter. So if you rotate this pi mode converter, this will give a rotational Doppler sheet for the OM carrying. And the same experiment can be replacing the quarter wave plate 1 and 2 by the pi/2 mode converters, right? So similar kind of things can be done. And there are suggestions. Okay. So now you come back to this, that so this spin to orbit conversion is actually mediated by the geometrical phase. Because as I said, that orbital angular momentum is related to the transverse distribution of the phase. Plane wave does not have any transverse distribution of the phase. And geometrical phase is polarization dependent. That means it is opposite for left and right circular. So geometrical phase connects the spin and the orbital angular momentum. That means if I have a geometrical phase which is spatially varying, that connects the spin angular momentum and the orbital angular momentum. And this is the one case of thing that we see in symmetric system, which is related to the azimuthal gradient of geometrical phase, which gives rise to intrinsic spin to intrinsic orbital angular momentum conversion. So they're in very simple system like focusing, scattering, etc. This has been observed. And of course, this is the case I'll again describe. This is using something called Q plate. People can use wave plates where the anisotropy axis is spatially varying. So this also introduces spin orbit interaction. Yes. Yes, so basically particularly focusing. So the repeating the question is that scattering and focusing, does it also change locally the states like spin or the orbital states? So for example, ideally it's a good question. Actually, if scattering actually can change also the local spin, right? So, but for example, that will depend upon the scatterer. So therefore, this is not ideally for example, scattering cannot be treated by pure spin redirectional Berry phase, because you will also have polarization change. So there are some mixed description is required. But in case of the dipole scattering, you can assume it to be like that. If you take a particle to be dipolar, then you can still go ahead, or focusing, of course, that is nothing. If you put an interface of any, let's say, any reflecting material, that will locally change the polarization also, right? So a propagating thing. Okay. So yeah, that's correct. Right. So the other variant is so something which we'll discuss, that intrinsic to extrinsic conversion, which is like the back action of the trajectory, like separation of the two spin components, which is related to again the geometrical phase gradient. Now along, let's say there are two ways it can take place. One is the momentum gradient, another is the spatial gradient. And all the meta surfaces, etc., that we will be talking a little bit, use the spatial gradient of the geometrical phase, and they have a lot of utility. The momentum gradient of geometrical phase also, I will give you some example. And the other thing is, this is intrinsic OM to extrinsic OM, which is called the orbital Hall effect of light, orbit-orbit interaction. So, so this is a very simple way if you understand that what we are talking about, that this rotating wave plate problem, that time varying geometrical phase. If we do, let's say what I have written, homogeneous anisotropic medium, you give you Pancharatnam-Berry geometrical phase. Inhomogeneous anisotropic medium, space varying geometrical phase, which will connect OM and the SAM. So that is what the spin orbit interaction is. So space varying anisotropy can lead to spatially varying anisotropy axis like that if you tailor it like this. So this will lead to the so-called spin orbit interaction. Now let us look at what we are talking about. We said that the geometrical phase, time varying geometrical phase is written as S minus S0, S minus S0 change in the spin angular momentum. This is the rotation rate, temporal rate of rotation. But if I just replace this temporal rate by the spatial rotation rate, then I get a similar picture, but in the space domain now. Instead of a temporal gradient, I get a spatial gradient, right? And therefore, if I take, let's say, a symmetric system like a cylindrical symmetric system, I can choose this coordinate xi to be, let's say, one of the azimuthal angle phi, and then this rotation rate, that is rotation rate in the space domain, is the azimuthal rotation rate, can be written like this. And if I can tailor this, like for example, if I can tailor this angular, so this variation of the orientation of the wave plate in the azimuthal direction separately, differently. For example, usually it is written as Q phi. So Q is called the Q number. So then this derivative of this will give you Q. So this resulting azimuthal geometrical phase will be something like that, right? Just like the temporal manifestation, you will now have Q phi S minus S naught. Now you see, so if S minus S naught is 2, this will generate a geometrical phase which is azimuthally varying, like 2Q phi. So this will generate the orbital angular momentum. So that is at the heart. For example, if you take Q is equal to 1, and if you take a half wave plate, it will give you an orbital angular momentum of plus minus 2 phi. That is exactly, basically, you have start with spin plus 1, go to spin minus 1, and you generate angular momentum of 2. And if Q is, let's say, something else, then of course some angular momentum will also be transferred to the material medium. Similarly, a vortex quarter wave plate, there will be one quantum of angular momentum will be transferred, and this azimuthal variation of the geometrical phase will be Q phi. So basically, you will generate azimuthal variation of the geometrical phase, which will give you like a spin orbit interaction. And that is what typically used in these so-called Q plates, that you can actually make the Q plates with spatial varying anisotropy axis. And if you use the simple Jones calculus, you end up in the same thing, like what we just using the analogy of the angular Doppler shift, that the time varying geometrical phase that leads to the shift of the frequency. Similarly, the space varying geometrical phase will lead to spin orbit interaction in the symmetric systems. So these are one thing. So as I was saying that this kind of thing has also been observed in the scattering and in tight focusing. The essential physics is the same, that it generates the azimuthally varying geometrical phase due to the trajectory of light. And also, as I said, that there are also the transverse caustics. So this geometrical phase variation can be either in the space domain or can also be in the momentum domain. And either case, in case of the time domain, it leads to a shift in the frequency. But if you break the symmetry of the system, then it will lead to a shift in the K vector, that is transverse K distribution. Let's say you take a Gaussian beam, it has a transverse K distribution of Gaussian beam. Now you will have a spin dependent shift of the transverse Gaussian beam, that is a momentum domain shift, which is generated by a spatial gradient of the geometrical phase. But you can also have a spatial shift if you generate a momentum gradient of the geometrical phase in this way. Of course, for symmetric system, there is no change in the center of gravity of the beam. But as soon as you break the symmetry of the system, for example, in the XY direction, if you introduce a gradient in the X direction, then your beam will be shifted in the plus Kx and minus Kx direction, something like that. So this is an analogy. So it is like, let's say, basically transverse gradient of geometrical phase for different plane waves forming a transversely confined beam. So it's, as I was saying, that many K vectors form, say, let's say Gaussian beams. So there are like many plane waves. Each of these K vector, if they acquire slightly different geometrical phase, that will lead to shift of the beam. It's just similar to the thing that you see, relative phase gradient between many waves, shift of the wave packet. It's like a wave packet shift. Yes.
What do you mean by space varying geometric phase?
Yeah.
Because you calculate geometric phase after some twist, right?
No, I'm saying that in the transverse, if you have followed this, so it is not the twisting case. It is basically you are talking about the other thing, that here the geometrical phase is coming due to the trajectory in the polarization state space, not in the physical space. Now that trajectory will depend upon the orientation of the wave plate, right? So it is not in the physical space, it is in the Poincare space. That is, there are two variants of the geometrical phase. Here in the transverse coordinate, let's say I take a beam and I take the transverse coordinate X and Y, and I specially tailor the orientation of the wave plate, then at each of these points you will have different geometrical phase, because the geometrical phase is decided by the orientation of the wave plate. And here, as I said, that in this case, the geometrical phase is not originating from spin redirectional Berry phase. It is coming from the Pancharatnam type Berry phase. That is how you can produce phase varying. Because otherwise, you will mix up these two. Okay, right. So, so this one, which I was telling that this is a shift of the wave packet. This is precisely the so-called spin Hall effect of light. And a very simple example of this, again, this I have taken from one of Bliock's paper. I'll give the reference later. That if you think that if you have a Gaussian beam falling into the interface and getting reflected, so this Gaussian beam has a distribution both in the plane and the perpendicular to the plane. So the in-plane distribution, I'll come later, but there is a distribution of the plane which is perpendicular to the plane. So for them, the angle of incidence is the same, but the plane of incidence will be different because there is an out of plane. Each of these plane wave, they are propagating for a slightly different plane of incidences. So to represent them in the central coordinate system, you have to apply those rotation matrices. And how they are deviating is basically given by the spread of the transverse spread of the momentum vector ky. And therefore, this rotation of the plane of incidence is proportional to the angle of incidence like that. Nu by sin theta, this nu is the spread of the momentum vector. So the more it is spread, the more it will be rotated with respect to the central plane. And this gives rise to the geometrical phase. And this geometrical phase will depending upon the ky, that is the transverse momentum. Each transverse momentum will pick up slightly different geometrical phase. So if you have a slightly different geometrical phase for each transverse momentum, then you Fourier decompose the beam and add that phase, it's exponential I, let's say some phase gradient, and then come back. Then in the real space, you will see a shift, right? And that shift is the so-called spin Hall shift of light. And ideally, you get a shift like this. Sigma is for plus and minus for left and right circularly polarized light. But due to the finite Fresnel reflection coefficients, you have some correction terms, which is Rp and Rs are the Fresnel reflection coefficients for P and S polarized light. It can also be shown that this comes from the angular momentum balance. Right. So there is, of course, another variant of the shift which is not related to the spin-orbit interaction. As I was saying, that there is also a spread, in-plane spread, and in-plane spread change the angle of incidence. And you know that for each angle, you have a different Fresnel reflection coefficient. So that will also change the distribution of the Gaussian beam. That will lead to a shift in the plane. The other one is perpendicular to the plane of the incidence. And this is called the Gu-Sanchez shift, and these eigenstates are linear states. The other case, of course, the origin was geometrical phase and their eigenstates are circular states, but here it is linear states. But ideally, just a little bit maybe, so this can be written in a kind of an operator formalism also by expanding the Fresnel reflection matrix in the Kx and the Ky components and defining the corresponding operators and using an unitary kind of evolution. That Ax and Ay are the corresponding operator for the Gu-Sanchez and the spin Hall shift or the invert feather of shift. And if you do that, these eigenstates will come out to be linear states, whereas the eigenstates for the Ay, that is related to the transverse shift, will be basically, ideally should be left and right circular polarization. In partial reflection, the shifts becomes imaginary angular value, eigenvalue, and in this operator formula, and we have k domain shift. So imaginary shift, imaginary value, eigenvalue means it's a shift in the conjugate domain, which is the k domain. In case of total internal reflection, you will get these two spatials. Okay, but ideally speaking, this spin Hall shift, which is more generally called as the invert Fedorov shift, does not have exactly left and right eigenstates, because as I said, that if it was like an operator of sigma y, like 0i minus i0, then its eigenstates will be 1i, 1 minus i. But because there are correction of Rs and Rp, the states are actually elliptical, right? And they have left and right eigenstates, and it is a little complicated, and it is also somewhat related to this physics can be related to the PT symmetry and exceptional point. But I just wanted to mention that the eigenstates are in the partial reflection case are not necessarily purely circular. They are circular when Rp and Rs are comparable. Otherwise, they are elliptical. And in the total internal reflection, the shifts become completely spatial, and the eigenstates becomes also left and also the diagonal projection, which is known as the spin Hall and invert Fedorov shifts. Okay, so the other thing, as I was saying, so this one, what we are dealing with this the spin Hall effect in simplest case of partial reflection, this is coming from the momentum gradient of the geometrical phase. There is also, which has attracted more more attention is basically by tailoring the Pancharatnam kind of Berry phase in the space domain, because that can be done using nanostructured materials. So what you do is that you generate spatial gradient of the geometrical phase, which leads to momentum domain angular shifts. So large shift can be generated here.
So that's like ordinary spin hole effect with spin current. Right? So in those are
So this is a classical analog, optical analog. So quantization will of course not come here, but you can get a similar kind of spin current also. So that is, if you just do the electromagnetic calculation, exactly it will give you the spin current. That of course, because you are using the classical electromagnetic field, the effect is purely classical.
so
Right.
classical I understand, but I'm trying to say will there be any
Quantized value, if you let's say do quantization of the field, then of course you can go into that. Because of course all this, when you do it classical beam, you can do analogous experiment with non-classical field also.
even when you are saying the in-orbit interaction coming from spatial variation of geometric phase, so there is a
No, there will be no quantization here, because this is just because you are defining it for a continuous field, right? And so that is how you are defining it classically. So there will be no quantization effect as well. This is a pure classical analog, you can think about like that. Okay. Right. So this has attracted a lot more attention, is that if you can, let's say the waveplate that I was talking about, that the orientation of the waveplate can be changed and you can generate a large gradient of the geometrical phase. If you do it in the nano domain, that is in a nanoscale, then you can generate extraordinarily large gradient, and you can generate large control of the beam. Let's say you can basically generate a large gradient. So using different angular momentum, you can direct beam in different directions. So that is the main motivation. So this what we call the anisotropic meta surfaces, which of course Professor Kapasho will give a talk that how this can be tailored. Just to give a simple example, that if you let's say take like say an anisotropic array of antennas like that, and that axis is let's say along this direction, which is like the optic axis of a waveplate. And if you can tailor this axis spatially, let's say you can put different arrays like in different direction, then you can actually generate this space varying geometrical phase, the fashion that you want, in the way that you want. You can exactly do that. And using simple Jones calculus that I had shown earlier, you can write it in a more general fashion like that. If it is a half wave kind of retarder, that means if you give a pi retardance, then it becomes very easy that it will start with 1i, that is left circular polarized light, it will become 1 minus i, and it will give you a geometrical phase which is given basically 2 alpha times xy. So alpha is the orientation angle. But it is true for any arbitrary waveplates. So let's say because in the nanostructures you cannot exactly make it, let's say delta is equal to pi. You can have any arbitrary value, but this will hold that there will be one component of the polarization, circular polarization, which will retain and which will not give you the geometrical phase. The other component will give. So therefore, the efficiency of this will be determined by the value of delta. Now, more it is close to pi, it will have more efficiency. So that is how it is done. So using this polarization control multifunctional optical elements like geometrical phase lanes, beam splitters, displacer, polarization aim sorter, modulator, etc. has been already defined. Some of which you may hear also from Professor Kapas's talk, if he will be giving possibly, hopefully he will give, right? So there are a lot of examples of that how this can be tailored in this. And another thing I was telling also that there is also that OM redirectional Berry phase, which can also be controlled in desirable fashion. And so thus far we have talked about the spin orbit interaction, which is only related to the geometrical phase, but there is another variant of the spin orbit interaction which will be completely unrelated to geometrical phase and which is related to the transverse spin and spin momentum locking, which Professor Gupta will be talking maybe tomorrow. And so why this field has become so attractive? So that is because that, as I said, that by tailoring geometrical phase in desirable fashion in these nanostructured materials, different kind of effects have been generated using classical lighting. Rotational Doppler effect I have discussed, optical Rashba effect, Rashba type of effect have also been has also been demonstrated, where you use the resonance of certain modes in this kind of systems. Plasmonic Aharonov-Bohm effect, quantum spin Hall effects analog has also been developed here. What is also more important, that using this kind of effects, basically you can generate nanostructured meta surfaces to control and manipulate light in desirable fashion. That is perhaps what is most the attracting point of spin orbit photonics, which will eventually lead to some kind of meta surfaces integrated in photonic chips, something like that, where you can actually tailor, control, and direct light using the angular momentum degrees of freedom of light. So that is what I have stated, novel spin orbit photonic devices by tailoring the geometrical phase. That is what it is attracting. Integrated nanophotonic on-chip integrable photonic devices, sensors, modulators, filters, optical isolators, display, data storage, quantum information computing, etc. In many places, this kind of effects are actually useful. The advantage is that you are using geometrical phase. So by default, these are dispersion free. And that is also if you can achieve tunability. And of course, tunability can be achieved through polarization, because by having polarization, you can also do it tunable. Flat and ultra thin, they are made in meta surfaces, ultra thin and of course on-chip integrable. So this is where we have been working, that what are the challenges in this domain are that of course many of the spin orbit interaction effects are rather weak. And in normal systems, they are rather weak. And many cases the quantitative understanding is lacking. So we desire, we do something, we measure, but how it depends on exactly what parameters, that is not very well understood in many cases. And the third is, of course, to achieve control and tunability. So the avenues, of course, is to tailor giant spin orbit interaction effects so that you can have a large control, tailor large spatial gradient of geometrical phase in nanostructured metamaterials, some of which I'm showing we are also fabricating such structures. Another, that is what I've written, nanostructured anisotropic medium, plasmonic and dielectric metasurfaces. And also another way which is we are using is SOI effects in hybrid metamaterials, so that you can have resonance enhancement and tunable, because resonance can be tuned, and in the near the resonance frequency possibly you can have a large enhancement of SOI. In some systems we have observed that. And also another avenue is combining nanostructured metamaterial with structured light to enhance and control from the same device that you make using structured light, you can have multifunctional optical elements. And another thing which we have been working is on weak measurement to amplify these tiny spin orbit photonic effects. So how much time I have consumed? So 5 to 7 minutes. I'll just almost through, or I've completed 5 minutes. Right. So this is the kind of the avenues that possibly we are also following, and many other groups are following, that to kind of have to enhance these effects, to have control and tunability, and also to have quantitative understanding on this. The number of papers which I will share, that which gives the state of the art of this field, and our book, of course. And just quickly, I want to finish in 5 to 7 minutes without going into the details. So let me also introduce our group. That our group is Biooptics and Nanophotonics group at IISER Kolkata. So we work on nanophotonics in the domain of polarization, angular momentum of light, spin orbit interaction of light, weak measurements. Also, we intend to develop plasmonic devices, sensors, and we also have an activity in the domain of biophotonics. And this is our current group. Some of the work, recent work, our students are giving posters. So Niladri, Samuel, Jivan, Annesha, so 3 of them are here, and Dr. Devdatta, so she is also here. She had, of course, exclusively worked on metasurfaces and during her PhD work, and we have many collaborators, of course. So basically, so this is a system that we have developed in-house, which is like the workhorse in our spin orbit photonics research. So this is a very specialized kind of experimental setup where we have integrated this so-called Mueller matrix, which I was describing, Mueller matrix measurements in a microscopic arrangement, and that too in a dark field arrangement. So the dark field arrangement is slightly special because you have in a bright field, of course, you have all the light. Let's say you have a condenser, all the light goes to the objective. So if you have let's say scattering from a nanostructure which is very weak, maybe it will be swamped by dot of direct light. So dark field arrangement helps in that. You have an annular condenser so that it focuses like in an annular shape, so that the direct light will miss the objective, it will not collect. Only if you place a nanostructured material, for example, here, the scattered light will go into the objective and it will be detected. With this, we have integrated our Mueller matrix measurement scheme, which is basically you generate 4 states here, you analyze 4 states here, total 16 measurements you do. So 4 different elliptical states you generate using a polarizer and a wave plate, and a polarizer. And it is related to a CCD camera for imaging, both in the real domain and in the Fourier domain. You also have, which is not shown here. So we also have a port which will record the spectra, so that you can also have spectroscopic studies. So this particular setup we have used for many spin orbit interaction effects and other effects in the domain of this nanophotonics. And we have demonstrated a giant spin orbit interaction effect in tailored metamaterials and hybridized metamaterials, demonstrated resonance enhancement and tunability in some cases. And this, of course, we have used weak measurement to amplify this very weak spin Hall effect of light. We have also developed novel concepts based on weak value amplification and weak measurement for this kind of hybridized metamaterial. As I was saying, that this is a particularly interesting metamaterial where you have a plasmonic grating. Below that, you have a waveguiding layer. So this is hybridized because the waveguide modes and the plasmon mode, they get hybridized. And where they hybridize, it will strongly actually enhance a lot of effects, including the spin orbit interaction effects. Here also we have used weak value amplification. And this kind of system also, we have shown that this leads to some kind of phanoresonance, which is also tunable. So therefore, by tuning phanoresonance, you could also tune the basically spin orbit interaction effect. There is a poster given outside by G1, I think, has a poster on that, showing that how in this hybridized metamaterials, the spin orbit interaction effect can be tuned and tailored. And this is a geometrical phase gradient meta surface, as I was saying, that there is rotating grating. So this can be used to actually directional guiding of light, etc. If you put left or right circularly polarized light, so they will be guided in different directions. And they will also lead to tunable phanoresonance in this kind of systems. And this is something we have observed, the orbit-orbit, pure orbit-orbit interaction effect, not spin orbit. So this is basically intrinsic orbital angular momentum to extrinsic orbital angular momentum conversion. We have also observed spin selective random scattering, which is related to the spin Hall effect in random medium, and in specially tailored random medium. We could observe this random spin splitting, spin dependent splitting of these modes inside a random medium. And yeah, we have also been working on the transverse spin and spin momentum locking, but this part not experimentally too much. And this one that I was telling, that recently we have seen a very interesting effect in this kind of hybridized system. A spin momentum spin locking, not using evanescent waves. Typically, spin momentum spin locking is, as I was mentioning, is actually done through the evanescent wave, which is completely independent of geometrical phase. But we have done using through the geometrical phase of tightly focused light. And we could see in the far field, because evanescent field you actually don't see in the far field. So this far field in the momentum space, we could see simultaneous spin momentum spin locking. That means forward and inverse spin Hall effect. That means that you come with one spin, that it excites waveguide in certain direction. And if you come with any arbitrary state of polarization of light, the waveguides excited in a particular direction will only carry certain spin angular momentum. So this is what we have named as spin momentum spin locking. So that is a direction dependent spin and spin dependent lightening up of the opposite direction of the waveguide modes. So this kind of thing eventually can lead to some interesting devices also. This is something what Niladri will be presenting here. The non-separability of the two variant of the shifts that I was talking about. Usually we treat them independently, but we have shown some kind of position classical entanglement relating to the non-separability of these two variant of the beam shift that I was discussing. So this is something on spin orbit photonic device. So this is, again, we call it a geometrical phase polarimeter. So one of the problem in polarimetry, as you have seen through the discussions, that you need multiple measurements, but in many cases, you may need to have a single shot measurement, right? That is maybe the dynamics you want to probe. So we have devised a method based on geometrical phase, because geometrical phase, or let's say if I have an anisotropic medium which is otherwise homogeneous, the geometrical phase will depend upon the input state of polarization. So if you can measure the space varying geometrical phase in an interferometric arrangement, you can measure the simultaneously a single shot measurement can provide you full information of the polarization of the light coming of any arbitrary polarized phase. So that is what we have demonstrated in this, what we named as geometrical phase polarimeter. We have also developed the concept of so-called weak value polarimeter. So which again using the interference philosophy of the weak value amplification, which I of course did not discuss. using this concept, we could actually detect very weak optical anisotropy effect. We could amplify anisotropy effect. Sometimes it is very difficult to detect, let's say, very small optical rotation. We could amplify almost by 100 times. And also we could have dramatic enhancement in the sensitivity of such measurements. So this, again, we named as weak value polarimeter. Something again like spin orbit interaction, microbeam reflector using spin orbit interaction of light. We have also been working towards developing sensors. So there is a plasmonic crystal meta device, again using this kind of spin orbit photonics meta device for sensing arsenic, so which we have recently demonstrated. Yeah, so that's it. We'll stop. And yeah, I'll be happy to answer any questions if there. These are all because we are working with mostly plasmonic materials, so they have resonances in the optical frequencies only. The waveguide modes that we are talking about, that is also in the. No, so meta, so again, these meta materials, sometimes people use it only in the context of suppose possibly negative refractoriness material, but that is not true. Meta material is something which is not naturally existing, but you can structure it to generate some functionality. Is in optical domain, all in the optical domain, all in the optical domain. No, the meta surfaces are purely in the optical domain, because it depends on that what kind of modes you are exciting. So the modes that we are exciting, like the waveguide modes or the plasmon modes, they have resonances in the exclusively in the visible domain only. So that is how we could do that in the optical. And actually now you see Kapas's talk, you'll see that all these meta surfaces, meta materials are all in the optical domain, but not the negative reflection materials that perhaps if you know, that is not. Meta materials in a sense that you generate new functionality by structuring the material. So all these are not negative in these materials. Yeah. Yes. Yeah, I will. So actually, the Heisman has some initial papers. So there's basically those spiral gratings, these plasmonic gratings they fabricated, which actually converted spin to orbital angular momentum. In additional to that, they also give geometrical phase, right? So Karimi's paper also. Karimi's papers are also there. Yes, because this will depend upon how you make the spiral. There are, I think, papers by Ibrahim Karimi and earlier by Heisman also. Heisman group, some papers on, they had only this 2 orders. But I think Karimi's group has more flexible and other things. Higher order things. Earlier, the first one I said that Heisman's papers, which was the, I think I would say the pioneering paper on this spiraling plasmonic groups, which converted left to right and then generated 2 L equal to 2. That was, I think, in 2010, 11 something. But Karimi's group has a lot of work on, recent work on this kind of. Liquid crystal is also there. Is this ATNA bracelets group. ATNA bracelets group has very interesting papers on, because in liquid crystal you can change the topology easily. But the advantage of the nanostructured materials is that you can do in, of course, in the nano domain. The liquid crystals you cannot. There are examples where people have combined the liquid crystal and meta surfaces also. Right. No, there was, so I'm saying the motivation was this, that of course you use SLM to modulate, specially modulate light, but there is a limitation, of course, because it is limited by the liquid crystals, pixels, etc. So they combine metamaterials. So the metamaterials, when it's nanostructured materials, so that is used basically as a control of the base refractive index. So that a similar kind of modulation principle, you can use that through polarization control of the materials. But liquid crystal has its own this thing. So they have combined these two to actually go to higher resolution using liquid crystal based devices. But ATNA bracelets group has a lot of interesting paper on spin orbit interaction of light in liquid crystal. In fact, the first paper, the PRL paper, was on a liquid crystal droplet, which first showed that these polarization singularities and the spin orbit conversion in liquid crystals. Following that, they have a series of papers on liquid crystal based. Yeah, but here actually these droplets, they have, so this, if you look at this, that anisotropic, because liquid crystal is also anisotropic. You see, the main trick is that you want to generate space varying geometrical phase. So, for example, Q plate, they are nanostructured materials, the wave plates anisotropic axis is spatially varying. In liquid crystal, you can actually control the director's orientation by chemical route or by some other routes. So that let's say you can make it radially like that, or you can make it azimuthally like that. So that means the optic axis will be varying like that. And that is any space varying geometrical phase will connect spin and orbital. That is the essence of using liquid crystals, because you can actually, in the same system, you can actually generate different ways. That is also the tunability that liquid crystal gives. In meta surfaces, that flexibility will not be there. Once you make it, and you have only control that, you can now control with the input light's polarization state. Possibly you can realize some different this thing, but structure you cannot change, of course. Yes, yes. Oh, that see this paper. Let me just yeah. So I did not talk about that. Is a very good science paper, which actually so this work that I was talking in disordered medium. There is a science paper on this that in completely there are also another paper in spin Hall effect in random medium, recent maybe a couple of years back, PRL paper. So this in random medium also, because as you said that there are also a lot of singularities by and they'll basically in the momentum domain they give a lot of spin split random modes. That is also very fascinating because there are also a lot of singularities around those spin split modes. Yes, yes, yes. It is very interesting. I'm sure it is very interesting. In fact, if you even meta surfaces, if you made disordered meta surfaces, it can actually lead to a lot of interesting effects. Yeah, you are correct. That is, I think disordered system is another one because see, in the context of condensed matter system, also disorder is very, very important here. Similarly, one would expect. Okay. Yeah, that is a good question. Actually, loss is a big thing in meta surfaces because particularly when you do metal-based meta surfaces, because the silver or gold they have a lot of absorption. Now, and because why you want silver and gold, because you want to explore the resonance, which is a plasmon resonance, which is very easy, dipolar plasmon resonance. But there are also now people are looking at the all dielectric meta surfaces. So dielectric structures also give resonances. These are the me resonances. So people are trying to exploit that because it is less lossy. But you are correct that in case of, because plasmonic devices, main problem is the loss, that of course the plasmon cannot propagate to a large distance. And when you are thinking about device, but still it is in some cases.
I was saying that even the adiabatic cyclic description of
so that no, but this is related to polarization loss then. So that is not related to the, see, whenever you are talking about no, so yeah, that's what I'm saying, that mostly these are polarization preserving. So loss in that case is not the attenuation loss, where if you see that the kind of Hamiltonian that I was showing, it is the evolution of the polarization. It is polarization loss is, yeah, in most of the cases it is minimal. But still, I'm saying that in the context of no, I'm saying that, yeah, so mostly this meta surface is using Pancharatnam-Berry type geometrical. because it is very difficult to tailor the trajectory in the nanostructure. It is too easy to tailor the anisotropy in the nanostructure. That is the rationale. So that's something that but he was initially saying. No, but I said that's correct. If there is depolarization, that will this adiabaticity will be affected. If you have depolarization. That let me just tell you a little bit. I did not want to talk about it. We have been also working on that. Where is that? Yeah. So basically, this shift operator, where is that? Yes. So ideally, this operator is like, if in ideal case, it is like sigma y operator, 0 minus I 0. So its eigenstates are 1 I and 1 minus I. This is an ideal case. But when you have a reflection from, let's say, interfaces, then you also have this Fresnel reflection coefficient Rs and Rp, which are not equal. So therefore, this becomes a slightly non-Hermitian system. And that all the physics of non-Hermitian system is actually involved here. So here, despite the system to be non-Hermitian, you will have real eigenvalues. So this is what exactly people are working on pretty-symmetric system and exceptional points. So this has left and right eigenstates. That's the similar way. But there are still something to work on it. But it is very close. It has some analogy with the non-Hermitian systems, where you have non-Hermitian system, but real eigenvalues. This is the kind of system that we're talking about. Crystalline means photonic crystal type of thing. So I see this. I'm telling you. So this is the. I did not, of course, I do not have. I think our work in our slides. So this is this periodic systems. This waveguide thing. So these are all like periodic systems. That's what we call the plasmonic crystals. It's called plasmonic crystals. Many of the physics, right? That is what also we are trying, because these are basically plasmonic crystals. You have 1D grating. Why is that? Yeah, so this is 1D. This is 2D. Yeah, so ideally, see, that's right. Ideally, geometrical phase is dependent on the orientation angle of the wave plate only, right? But the problem is that when I say that this is correct, that ideally it is, but the problem is that it is not also perfectly correct, because the wave plate, but it will still give geometrical phase. Let us go to this equation. I'll tell you that. What is that? So this delta value, which is a dynamical quantity, right? Delta is the birefringence. That is not wavelength independent. Orientation is wavelength independent. So as you move on from wavelength, the efficiency will change. Efficiency of SY will change, but the geometrical phase might not change. Right? But of course, this is also a problem, but still better. Better that it is ideally dispersion free. It is a metasurface. So it is basically, I have just written it for only one unit of the metasurface. You repeat it, this alpha will now vary as a function of position in a nano scale. That becomes a metasurface. Yeah. Okay, thank you. No. Oh yeah. Hi, you just saying that. Geometrical phase in this kind of system, it depends only on the orientation angle. As I was saying, no, there is no fixed thing like that. So basically, as I said that in Pancharatnam phase, it only depends on the orientation of the plate axis. So you can actually in principle get limited to, of course, 0 to 2 pi, because after that you cannot discriminate it. But even in spin redirection very phase, there is no such fixed number that you can. So that may be a practical difficulty somewhere, and also, of course, 1.7 that you see this 2 beta, geometrical phase is 2 beta, so you can also not go. So, but you cannot also go on a very large. What is important is that you generate a large gradient. That is important in this in the context of meta surfaces. Absolute value of the geometrical phase is not important, but the gradient of the geometrical phase is important. And nano is this meta surface is attracting a lot of attention because you can tailor that in the nanoscale so that the gradient is very large. In the micrometer domain, the gradient is low. But if you go to the nano structures, the gradient is very large. And the value of geometrical phase perhaps is not very important. It's the gradient that is important. Yes. So see, that is why I'm saying that if you have a meta surface material, so it is depending on the orientation. Now, if you tailor the beam, because see, if you have a specially structured polarization passing through a homogeneous anisotropic medium, that will also generate geometrical phase. Now, if you combine them, then you can actually play around with that. Right? And also by tailoring light, that light is. Yeah, because of the complexity of the representation, because it is a higher order Poincare sphere, we tell it, but to define a geometrical phase in a mixed state is little, not that very simple, not that clean. But yes, what Ranjan said is correct, that you can always use active thing to control also. But I'm saying that what is important is that the gradient in the context of this in-orbit photonic devices, gradient is most important. Either you a momentum gradient, sorry?
Not bother with the value of geometric phase.
But if it is very small, of course, very difficult to.
No, you are not, because
gradient is important.
Value
is quantity. Is the gradient is important in this context. Right. Thank you.